Good morning and welcome to week 7 of Logic. And this week we're getting into a little bit more deeply into propositional logic. On Thursday or Wednesday of last week, I posted the video introducing the basic symbolism for propositional logic. And your readings for this week cover the basic truth tables, that is, a diagram of all the possible combinations of true and false for each of what are called the main connectives or the uh, main symbols that we will be using. The purpose of this little lecture this morning is just to go through some of that with you and also to clarify what's on your list in terms of assignments for this week. So uh, I'm not asking you to do every assignment in the Gensler book. Part of the reason for that has to do with Canvas and the symbols, and I won't get into the details, but it's not straightforwardly easy to work with the symbols on Canvas, and some of you don't have access to Logicola, unfortunately. So I've done two things. One is to cut out some of the work from the middle section of this chapter on propositional logic, which would have required you to write out the truth tables using the symbols and so on. I've given you exercises in which the goal is to calculate the overall truth value of formula. If you've reached that point, all I'm asking you to do is simply to say overall, is the truth value true or is the truth value false for the statement that you're given. Later in the chapter, we will be using truth tables and other methods to determine whether or not an argument is valid. In that case, I will just, you can do the work on your own, write it out is what I would do with paper and pencil, and then turn in the result. Now, I did also send out some symbols from Gensler's webpage that you can cut and paste. I will give you a few assignments in which you'll have to use those, but I'll try not to overburden you with cutting and pasting symbols while still helping you learn the techniques and learn propositional logic. Okay, so I want to rejoin Gensler, roughly where we were last time, using the slides. So let me share my screen. Okay, so using the supplementary materials that are found on the page. Here it is. And on the page that gives you the Logicola download, at the very bottom, if you're interested, there are sets of slides that you can practice with, and there are also some flashcards and other supplementary materials to help you to learn the basic symbolism and how to use it and so on. Okay, so we had just reached the first truth table for the and. So remember the dot means and. And I should also explain that Gensler has adopted a convention which is not at all standard, of using a 0 to mean false and a 1 for true, rather than T and F, which is the usual method, usual convention. The reason he does that will become clear a little later. But you just, excuse me, have to get used to using 0 to mean false and 1 to mean true. Okay, so let's just go over this basic truth table again. How is a truth table set up? Here are the two parts of this statement. The overall statement is called a conjunction. The parts, P and Q, are called conjuncts. The dot is what this symbol is called, and it is the main connective of the statement. So the statement is called a conjunction. Its parts are the conjuncts, and the dot is what joins them together. Remember, with the dot, we always use parentheses. Never use any of the connectives other than the squiggle without parentheses. So what this is telling us, we alternate zeros and ones in the first column under Q, and then 0, 0, 1, 1 under P. Remember, 0 means false and 1 means true. And what we get are all of the possible truth value combinations for the statement P and Q. And what this first line says is that if P is false and Q is false, the statement P and Q is false. If P is false and Q is true, the statement P and Q is false. If P is true and Q is false, the statement P and Q is false, right? Because what the statement means is that both are true. So the only way it comes out true is this final line where we have P true and Q true, then P and Q are true. So this is, in a way, it's just making very explicit and very clear what is meant by P, affirming P and Q. Well, it means that both P and Q are true. Okay. The or sign is the V. It's called a disjunction, and its parts are disjuncts. It's a little less clear when you first look at it what the truth values should be, because in English we use or in an exclusive sense often and in an inclusive sense. In the exclusive sense, it means P or Q, but not both, or this or that. In the inclusive sense, it means P or Q or both, right? So we're using this in the inclusive sense in this truth table. So obviously P or Q is false if both disjuncts are false. If P is false and Q is false, then P or Q is false because one or both have to be true. It's claiming less than the dot. The dot says both have to be true, whereas the V says one or the other or both, as we'll see. So the rest of the lines come out true. If Q is true and P is false, then P or Q is true. If P is true and Q is false, P or Q is true. And here's the one that often trips beginners up a little bit, is if P is true and Q is true, P or Q is true. Okay, so the way to think of it is, as Gensler puts it on the slide, at least one part is true, but both may be true. So don't let that throw you off because you're thinking of the English conventions around or and the possibility of the either or, the exclusive or. Whereas this is the or that we use when we mean it's one or the other or both. Okay? Next is the horseshoe symbol, which is called a conditional. This is a very important symbol for later. It's worth thinking about it carefully. And it too, at first, is not as intuitive as and probably not even as intuitive as or, in the sense that we really have to memorize, I think, at the beginning, this truth table in order to work with it. Okay, so what the horseshoe means is if then. So if I went to Paris, then I went to Quebec, we can symbolize with if P, then Q. Okay, if P, then Q. I'm going to go over these rules at the bottom and explain just a little bit about the workings of this particular truth table. But again, my recommendation is to simply memorize it at the beginning. And then as we work with it, as we go through exercises and learn methods that use the horseshoe symbol, use the conditional, then we'll start to think more philosophically about it and try to understand why the truth table comes out the way it does. Okay, so first line, if P is false and Q is false, if I went to Paris, then I went to Quebec. If both Paris, if I haven't gone to either, you might think, oh, well, then the whole thing is false because it has two false parts. The parts, by the way, are called the antecedent that comes before the horseshoe and the consequent that comes after the horseshoe. But if we were thinking that way, that if both are false, then obviously it's false, we would be mistaken. The rule of thumb at the bottom is that falsity implies anything. So if the antecedent is false, we are going to know right away that the whole statement is true. So if both are false, it's true. If P is false and Q is true, it's true. The only, and this is the important line, the only case in which the whole if then, the conditional is going to come out false, is the case in which the first P is false and Q is true, then the whole thing is false. If P is false, all right, sorry, if P is true and Q is false, if P, then Q is false. And of course, if both are true, the whole thing is true. So memorize first, and then look at what Gensler has for us in this box. These are handy rules of thumb to recall when you become confused about the if-then, about the conditional. First is falsity implies anything, so that if you have a 0 or an F, false first in the conditional, you know the whole conditional is false. The second is that anything implies truth. So if you don't have the first part, if you don't have the antecedent and you have true, right? It's true. And then truth doesn't imply falsity. So again, what you have to remember is just that the only case in which it comes out false is if the first part is true and the second part is false. Actually, there should be I don't know why he has this blank. What he really ought to have on the slide is the false, right? To mirror the second line here. So anything implies truth. If you have the second part true and the first part false, it's going to be false. If you have the second part, obviously, if you have both true, it's going to be true. Oh, I think I misspoke. So again, if the first part is false and the second part is true, it's true. If the first part is true and the second part is false, it's false. And again, this is the only case in which it comes out false. So you know, if you see true in the second place here in a conditional, that the whole thing is going to be true. Anything, which is what he's meaning here by anything implies truth, which is just a useful way to remember the basics of this truth table. So think about the truth table for a while for the conditional, because this is the definitely the one that gives students at the beginning the most trouble. The easiest way to memorize it is just to focus on the one case in which it comes out false. And that again is if the antecedent is true and the consequent is false, the whole thing is false. Get in the habit of using these terms, antecedent and consequent also, and your thinking will become clearer, I think, about the condition. The next symbol, I don't think we use much in the early exercises. The 3-bar means that both parts have the same truth value. It's called the if and only if, or the biconditional. Sometimes it's symbolized by an arrow, a two-sided arrow, meaning that the implication runs in both directions. It is not an if-then statement, but an if and only if statement. And it is true just in case both of its parts have the same truth value. So if you understand what it means, both parts have the same truth value, then you will right away know what the truth table should look like. It's only true in case P is false and Q is false, or P is true and Q is true. I hope that makes sense. Okay, so your work for this week is really just taking you through these truth tables, the basic truth tables, and then asking you to work with them a little bit in determining the truth value of a statement, given the truth values of its parts. So let's look one more time at that tricky conditional so that we don't forget that. So let's just go through it again. If P is false and Q is false, what is the whole conditional? True. If the first part is false, we know it's going to be true, right? If P is false and Q is true, the whole conditional is true. Here's the one to watch out for. If P is true, first part, antecedent, and Q is false, then the whole thing is false. If P is true and Q is true, the whole thing is true. Of course, it doesn't matter, right, what letters we use. What matters is the position of the term, the letter, in the statement. So the first part is the antecedent. If the antecedent is true and the consequent is false, the whole thing is false. Otherwise, any arrangement gives us a truth value of T, or in Gensler's book, 1, meaning true. So just to clarify a little bit, part of what Gensler is doing with the 1s and the 0s is that he thinks, and it's probably true, that it is easier to see a pattern like this, 1, 0, 0, than it is to see, if you're working out a long proof or a truth table, to see a T, F, F. So 1, 0, 0 is easier for us to pick out visually. Okay, I'm going to stop sharing for just a moment and then go to the text and show you some things. Okay, so the basic truth tables are what you're working with for this week. There is an assignment that I skipped over that asks you to translate from English into propositional. My advice is that you do practice with that a little bit. If you're using Logicola, that's an easy way to do it. If you're not, just look through this exercise. There are responses, answers in the back of the book for selected questions. And just make sure that you're translating consistently. It is important that you know how to do that. But again, the problem with the symbolism is going to make it extraordinarily cumbersome for those of you who are using the book alone rather than Logicola. So I'm not going to ask you to do that. 6.2 takes you through the truth tables that I was discussing with you just a few moments ago. Read through this, and it does exactly the same thing, even using similar or the same examples. Explains truth tables, logical diagrams, or pictures of all of the possible truth combinations for, at this point, the basic symbols or the connectives. So, and, again, oops, sorry. Yeah, here we are. Or a discussion of inclusive or exclusive or, which shows you how to symbolize exclusive or, but emphasizes that for the basic truth table, we mean this one. Exclusive or requires longer symbols. And here is our friend, the conditional. Again, if P then Q, Gensler writes, claims that what we don't have is the first part true and the second false. So he talks about, and I'm going to gloss over this for the moment, but he does explain in the text a little bit with respect to why the table for the conditional is the way it is. And so he ends here with the biconditional. And of course, the negation. The negation is quite straightforward, right? The truth table is just this. If P is false, then not P is true. If P is true, then not P is false. He did not include that one in his slides, but just so you see it, and it should come as no surprise, this is the way the truth table works for the negation. Okay, so once we learn and have interiorized, as it were, and memorized the truth tables for the connectives, we can easily calculate the truth value of any statement that we're given, right? So what these are asking you to do is just calculate the overall truth value of each formula or each statement, each proposition. Perhaps we should use the term proposition since this is propositional logic. They're used roughly equivalently, and Gensler usually favors statement, but philosophers also like to use the term proposition. So we're symbolizing a proposition. What does this proposition symbolize? Well, it's V statement, and so it's an or, and it's just asking you what the overall truth value is if one side of the V is false and the other is true. And of course, if you recall the truth table that we just went through, we know that the only case in which the or is false is if both sides are false. So what it means is at least one is true. So the overall truth value is true. How about the second one? What if you have two false statements joined together by a dot? Meaning this false thing and that false thing are both true. Well, two falsehoods don't add up to a truth, right? So the overall truth value of this, false and false, is false. Uh-oh, here is the horseshoe, or the if-then. The if-then, remember, comes out false only on the line in which the antecedent is true and the consequent is false. So this one, unlike in number 2, where we thought how absurd, right, that two false things could be true, in this case, if you have two false parts of a conditional, the whole conditional is true. So if false, then false, true. Not false. Well, you just reverse the truth value and it's true. The 3 bar is easy to remember if you keep in mind that both sides have to look exactly the same. So if both are false, it's true. If both are true, it's true. But if you have different truth values on either side of the 3 bar, it's false. So 5 is false. I think you're getting this now, right? 6 is, you tell me. It's false, right? Both have to be true. 7 is true because it's not what the one that we're looking for is if 1, then 0. But of course, intuitively, it makes sense that if both parts are true, that the whole conditional would be true. 8, compare with 5. In this case, we do have both sides true. So these are fairly simple once you have a grasp on the basic truth tables, the truth tables for the main connectives. And I think you should do fine with this. If you're turning in your homework on Canvas, you can simply write out the numbers and the overall truth value. You wouldn't have to do anything other than that in this case anyway. Some of the later exercises get a little more complicated. None of these are. Okay. So we can use that basic approach and determine more truth values in more complicated cases by substituting 0 and 1 and keeping in mind the rule that, and this is going to be important for a lot of things that we do from this point forward, in propositional logic, when we're working with parentheses and we're trying to calculate the truth value of a statement, we always work from inside out. We start inside the parentheses. So in this case, it says a true or a false. That's true, right? But the whole thing is false because of the squiggle or the tilde. So you work from the inside out. So the formula, not true or false, replace with, we're working from the inside out. So true or false becomes a 1 or true, which becomes false, right? He's just taking you through the steps here. Again, if you do this systematically, it's not difficult. Keep in mind, do not distribute. This is a common mistake because of things that we learn in mathematics. We um, think about distributing the squiggle to the individual terms inside the parentheses, but you would get the wrong result that way. Do not distribute not is the maxim that he gives us here. Do not distribute not. Okay. So we can calculate the truth value of these more complicated statements if we keep in mind that we have to start inside and work out, and keep in mind as well that we don't distribute the squiggle. All right, well, that's all that I have for today. I'm going to allow you to work on these this week on your own. Definitely, if you have any problems this week and would like to talk about the material, it is a little different. It is asking you to do something much more abstract in a way than the last couple of chapters, in that we have to learn to work in this new symbolic propositional language. So I understand that you may be having trouble. You may struggle a little bit at the beginning. So if you would like to meet individually with me, I'm available, or I will make myself available to meet. Otherwise, I will be scheduling a Zoom session at the end of the week. Have a nice week, everyone.